Hi, so here we're going to prove lemma 2.2 of this paper. I'm going to call it the gluing or bridge lemma. And that's because this lemma will be used in the proof of our main theorem to glue together this collar that we constructed to an outer Schwarschild region. This lemma is going to be exactly how we glue these. Once we modify this Schwarschild region, we're going to glue them together using this lemma. I'm going to state it more generally, but we're going to use it very strongly. So for this lemma, we have two functions defined on different closed bounded intervals, f1 and f2, that are going to be smooth, satisfying these three properties. One, we want each function to be positive, each derivative to be positive, and each second derivative to be positive on the intervals. And we want this condition to be satisfied. This looks kind of strange, but we'll get to exactly what this means momentarily. Basically, the second derivative should be less than this quantity, 1/2 times f, all times 1 minus f of t to the minus 2 times f prime of t squared. I'll get to what this means momentarily. This third condition is that basically f1 should be smaller than f2 everywhere. Recall that these functions are increasing, so this is that condition. And that the derivative at the left endpoint of the second function, that's this guy, should be the derivative of the right endpoint of the first function. So then, what's the statement? After translating the intervals so that, well, this condition is already given here. These two things are equal, but they should be equal to the slope between the right, I always get these mixed up, between the left endpoint of the second interval and the right endpoint of the first interval. I think this picture should do it justice, exactly what's happening. Here's the first function. It's increasing, it's positive, it has positive second derivative, and the same goes for this function. This slope here at this point is equal to this slope here. Well, maybe it isn't, but it's supposed to be in my drawing. And so we're just going to linearly interpolate between them. And that's exactly what this condition is saying, that we can do that. That the slope between these 2 points is equal to the derivatives at the endpoints. Then what can we do? We can construct a smooth function. Basically, this smooth function f is going to be defined on the entire interval, the entire of a1 to b2. And it's basically just going to slightly modify f1 and f2. It's going to satisfy these conditions. It's going to be positive. It's going to have positive derivative. It's going to be equal to f1 on the first part of the first interval. It's going to be equal to f2 on the second part of the second interval. And this metric, f of t squared times g star is round metric, recall, area 4 pi, plus dt squared, has positive scalar curvature on the sphere times the interval. So now, I've written these separately. So condition 2 up here and condition 4 down here really are saying the same thing. And that's what this fact is. I've written them in two different ways so that I could talk about it here. That the metric ft squared g star plus dt squared on S2 times an interval has positive scalar curvature if and only if this condition is satisfied. So that's this condition here. So really what this is saying is that each of these functions, when written like a metric like this, has positive scalar curvature on the manifold S2 times A1 B1 and S2 times A2 B2. So basically what we're saying is we're going to take this collar we constructed, has scalar positive curvature, and the Schwarschild region has scalar positive curvature, and this rightmost interval is going to serve a purpose on the Schwarschild region, and the leftmost interval is going to serve the purpose of the right side of the collar, and we're going to glue them together. I will denote this value by capital omega sub f of t, just for simplicity. So let's begin the proof. As I mentioned before, we're going to let f tilde be an interpolation of F1 and F2. So in other words, this drawing again, we're just going to interpolate between these 2 points. Then F tilde is strictly increasing and is actually C11 on, well, let me just write it once here, on A1 to B2. Now, for any sigma bigger than 0, we're going to let, this is sort of what I mentioned, we're going to smooth out F a little. We're going to let F sigma be a mollification of F tilde. Excuse me. And obviously, as sigma gets smaller, F sigma is going to approach the value of F tilde. And we want to do this in such a way that we leave the function fixed on, well, we want to leave it fixed on the first part of the first interval, so on A1 plus B1 over 2, and on A2 plus B2 over 2 to B2. So in other words, F sigma will equal F tilde here, and it will equal F tilde here. But otherwise, we're going to just smooth it out slightly, still keeping it positive, and satisfying these other conditions. So let me just move this out of the way and get myself some more space. How can we do this? Well, by assumption, the second derivative of Fi of t is less than this capital omega, that quantity that I defined, Fi t, for all t and Ai Bi. This is the condition that these two metrics would have positive scalar curvature on S2 times their intervals. So let D be the minimum over, well, I equals 1, 2 on the interval Ai Bi of this value, capital omega, Fi of t minus Fi double prime of t. And so we've just established that this is bigger than 0 because this is over a compact set and everything is positive. Since F tilde is in C11, we know that F sigma is going to converge to F tilde in C1, just by properties of mollifications. So therefore, capital omega F sigma approaches capital omega F tilde uniformly. So we can arrange, so for sigma small, arrange for this to be within d over 2 of this. So in other words, let's say the supremum over t of omega f sigma minus omega f tilde to be, well, less than d over 2. And we can do that. Now again, since f sigma is a compactly supported mollification, we can take sigma small enough so that f double prime sigma is within d over 2 of, no, we have a little bit of a problem here because, well, f tilde is not C2, it's not twice differentiable, but it is on A1 to B1 and A2, B2. Okay, so I'm still continuing. Is within d over 2 of f double prime on these two intervals, and is within f tilde double prime on, well, I don't want to say f tilde double prime, but I want to say 0, because that's really what f tilde double prime is going to be, but I want to do it on this closed interval, b1 to a2. So really f tilde double prime is 0 on this open interval, but f tilde double prime doesn't exist at these endpoints. But it's just a slight technicality that I'm not going to talk about anymore, but this solves it. So then we'll have f sigma double prime less than f tilde plus d over 2, which is less than or equal to omega f tilde minus d over 2, which is less than omega of f sigma. And in fact, this completes the proof.